So we can start off talking about exoplanets, the most recent stuff we did, and then we'll kind of work backwards, do a little bit of like inflation, dark matter, cosmic microwave background. I'm not going to have time today to go over the stuff that we did in the beginning, the types of particles and some of the hot Big Bang stuff. If you missed a section on that or want to review it, I did put a video up on that stuff. So that you should have the link to that. Let's see. So, exoplanets, there are a couple ways that we detect them. Some of the most common ones have found a lot of exoplanets, and then there's a couple that have just found a little that are kind of still developing. So, a big one that we talk about is the radial velocity method. Is that readable on there? No, it's not. That's better, I guess. So, normally when we think of a planet going around a star, we think of the star kind of holding still and the planet going around it. But what's actually happening is both of them are revolving around what's called their center of mass. So this is the idea: if you balance their two masses with the distance from some point between the two, you balance them out. So if you have a big star and a little planet, somewhere along between the two is going to be their center of mass. So the mass of the star times the distance from the center of the star to the center of mass is going to be equal to the mass of the planet times the distance from the center of planet to the center of mass. So the mass of the star is really big, right? And the mass of the planet is small. So in order for these two sides to balance out, that means that this distance has to be small and this distance has to be big. Right? Does that make sense? You have to have one big thing and one small thing on both sides of the equation for it to equal out and balance out.
Can you say what the distance is again? The
distance is from the center of whatever object to the center of mass.
Okay.
Right? So for something like this, where you've got a big star and a small planet, the distance, the center of mass is going to be something like over here. Right? It's on the line between the two. And you're going to have a small distance from the star and a big distance from the planet. Sometimes the center of mass is even inside the star if you have a big enough star or a small enough planet. Like for the Earth and the Sun, the center of mass is actually inside the Sun. So it's not at the center, but it's inside the Sun. So when we say that the Earth is going around the Sun, that's pretty much true, because it's going around a point that's inside the Sun, but not the center of the Sun. And the Sun is also going around this point that's inside it. So it's like, let's see, I'm gonna need a sharper pencil. It's going around a point that's not at the center, right? So it's still revolving, and it's not always the same, right? It's not just going around the center and it always looks the same, right? As it goes around a different part, you've got more on the bottom or more on the top because it's going around a point that's not in the center. So if you're measuring the velocity of the center of this star, like the center of the star is going in a circle around this center of mass, which would be where this is, right? So when we are measuring the star's velocity, we're measuring the velocity of like that center of the star. So we can, it's not just not moving at all, right? It's going around either the center of mass or some point that's right outside it. So we talked about when we had binary star systems, you had, let me make sure this green is showing up, kind of. you had, two stars kind of orbiting around each other. And you would get this graph that looks like this, right? The smaller star, the less massive one, would have a curve. And then the more massive star would have a curve like this. And these are their velocity curves, or radial velocity over time. So this is how fast this star is moving towards or away from an observer. So if something is going in a circle, right, sometimes it's moving directly towards the observer. Sometimes I'm not moving towards or away you guys at all. Sometimes I'm moving away from you guys. Sometimes I'm not moving towards or away from you guys at all. So that's why it goes, away to not moving at all, to moving towards, to not moving at all, to moving away. That's what this up and down shape comes from. So if we have something different, so we can kind of expand this out and say, well, what if instead of a big star and a small star, we have a star and a planet. And then this thing turns into, a much bigger curve. But even more so, right? This planet is moving a lot more than this star is, right? The Earth is going in a much bigger circle than the sun is, kind of just moving around. It's moving around that center of mass, right? This is a pretty small circle that the center of the sun is making, and the Earth, meanwhile, is going in a big circle. You have a much bigger curve. So, when there's two stars, we can look at both stars, we can catch their light, and we can measure their velocities. But when there is just one star and a planet, the planet's not giving off its own light, so we can't really see the planet. So instead, we just see a star doing this little curve all by itself. Right? It's just got this motion. And we say, okay, this star is rotating with something, right? Because this motion comes from rotating around the center of mass that you share with another object. So we know that this star is rotating around something. We know it's a small curve, so we know that it's not rotating around, a black hole, because that would be, 4 or 5 solar masses sometimes, and that would give a bigger curve. So we know that it's rotating around something small. We can't see it. Must be a planet. So this is one way that they can find planets, is this rotational radial velocity method. And this finds planets. It's easier to find big planets because big planets pull on the star more, right? The star is pulling on the planet and making it rotate, and the planet is pulling back on the star and making it rotate a little bit. So a big planet makes a bigger rotation. It's also easier to find planets that are closer into the stars. This is a question that you asked the other day. So when a planet is closer into the star, their center of mass moves closer to the star as well, right? So if this gets smaller, this has to get smaller as well to balance out. If one side of the equation is getting smaller, the other side has to get smaller as well. So if the distance to the one goes down, the distance to the other has to go down as well. So if this planet is close in, then this star is doing a smaller circle. But if it's doing a smaller circle, it's moving faster. And it's easier for us to measure that quick movement, right? Instead of going in a big, slow circle, it's turning in a really fast, small circle. And since we're measuring velocity, it's easier for us to measure these fast velocities. So we measure more big planets and more closer in planets using this method. Okay? The other thing about this is that in order for this method to work, we have to be looking at this system kind of from the side, right? So if you've got your star here in the middle and your planet's going around the edge of this, right? We need to be looking at it from an angle like this so we can see the star moving and rotating. If the star is going like this, like the planet's going around the edge and the star is moving in its circle, it's never changing how fast it's moving towards or away from us. And that's what we're measuring. Does that make sense? Right, so you have to be looking at it from this kind of angle. It can be like this a little bit because there's still some movement towards or away from us. But if it's like this, this star is never moving towards or away from us. It's just moving in a circle kind of in front of us. And we can't measure that. We can only measure towards or away from us. Okay, so that's kind of one of the limitations of this method, is that you have to be looking at it from an angle like this.
What's that angle called?
They just call it like edge on a lot of times. Instead of like this would be like face on. This is edge on. Okay, so that is the radial velocity method. Another method that is super popular because of this satellite called Kepler is the transit method. And this is what has found the most exoplanets to date because they used it for a satellite that was up for many years and it detected thousands of exoplanets. And so the way that this works is you have your star and it's really bright. And we measure how much light is coming off of this star. This is called a light curve. So if the star is just, if there's no planets, nothing happening, the star is just sitting here, then this is 0. Then the light curve is always going to look the same, right? It's always giving off the same amount of light over a short period of time. If we look at this star over, a period of tens of thousands of years, it's going to get a little brighter or something. But if we just look at it over a period of a couple years, it's going to give off the same amount of light. But if there is a planet that comes in front of this star and passes between us and this star, it's going to block out a little bit of the light from that star while it's in front of it, right? So while the planet's over here, it's not blocking any light. But as soon as it starts to get in front of it, and all while it's in front of it, it's blocking off some of the light. So the light curve from the star actually looks like normal, and the planet's in front of it and it goes down. And then once the planet's back over here and going around, or behind it, it goes back up to normal. And then the next time the planet comes around, it dips down again. So you get this very consistent pattern of dips every time the planet comes around. So these should all kind of be the same shape and distance apart from each other. Right? Because the planet is just blocking some of this light from the star, so we see a little bit less light. It's a little bit more complicated than that, but that's the essential idea behind this transit method. Right? And we can use this. So again, this is easier to find big planets because they block more of the light. Right? A bigger planet's going to block off a bigger fraction. So this only blocks I made it look like a lot, but it really only blocks like a teensy tiny bit of the light from the star. Because this is not to scale. Like the star is going to be a lot bigger than the planet. I don't know if you guys saw a couple weeks ago, there was a transit of Venus or Mercury where it went in front of the sun. And there's some really cool pictures, but it's just like a little dot in front of the sun. So it blocks like very little of the light. So this, would be 100% of the light. And then this is like, 99.5% or less.
Would it be the case that if the star was closer in as well, it would block more of the sun, more of the light?
Right. Yeah. So just by kind of that proportionality, if something's closer in, it appears bigger. So bigger, closer planets can also be more easily detected. We can still detect smaller planets, some smaller planets and some farther out planets, but it's easier to detect bigger, closer planets. So the other way detected massive planets better, right? Planets that pulled more for the gravity. This one preferentially detects like size, radius, and those kind of go hand in hand. Generally, if you have more mass, you're going to be physically bigger, but it is kind of a distinction. This one is going to more preferentially detect like radially large planets. Okay? So this is the transit method. You just block a little bit of the light, and it gets a little bit dimmer, and then goes back to being bright, gets a little bit dimmer, it goes back to being bright. This is the most common method because of the Kepler mission. A couple other ways that we detect planets. There's something called direct imaging. This is pretty rare, but it's really cool because it's the only way we can actually like see an exoplanet. And then for that, you have your star and your planet. It has to be going around like this. So now we have to be looking at it like this. So the planet's going around the edge for this direct imaging. And they just block out the light from the star, and they can see a little planet going around. So they haven't found this many planets with this. It's a pretty difficult method, but it's really cool because we can actually like see planets this way, see exosolar planets. So kind of just to go back for the transit method, again, it needs to be in kind of this configuration because the planet needs to pass between us and the star in order to block the light out, right? If it's like this, the planet's not going to come in front of the star from our view, so it's not going to block the light. So the transit method and the radial velocity method both need to be like this. Direct imaging needs to be more like this. There's a method called astrometry, which deals with proper motion. That one's not used very much. And then another method is the gravitational microlensing. So the idea behind that is you've got a star and it's giving off light in all sorts of directions, right? Just imagine I drew that all around.
What is this called?
This is gravitational microlensing, right? So if we're right here looking up at this star, we're really only going to get, you know, the light that's pointed directly at us. So we're going to measure just a little bit of the light from this star. And this light over here is going to go off this way. And that's going to go off that way. So the only light that we're going to receive here is just kind of the light that's pointed directly at us. But we talked about with general relativity in the last part of the class how something with mass can warp space-time, and light will bend around things that have mass. So if you have a planet that has some mass that comes in right here, it can bend this light. So instead of going straight out this way, it's going to curve around the planet and come to us. So all of a sudden, when this planet is between us and the star, we're going to get more light from the star, because light that would have gone off in other directions has bent around that planet and been directed to us. So this star gets a lot brighter when the planet is in front of it, because we're getting more light from it. Right? The planet blocks just a teensy tiny bit of light from the star, and it more than makes up for it by bending the light that would go off this way around this planet, bends this way, and comes straight to us. So we get all this light and this light and this light instead of just this, but only when the planet's right between us. So the star goes from being whatever its normal brightness to a lot brighter, and then back to its normal brightness when this planet passes away. So again, for this to work, does it need to be like this or like this? This way or this way? Edge on, right? Because the planet has to come between us and the star for this to work. Right. Okay, so that is detection methods for exoplanets. So most, like I said, it's the two most common methods. Both of them are a lot easier to find close-in planets that are large. So most of the planets that we found are like Jupiter-sized, and most of them are really close to their stars, like very close into their stars. And most of it looks like we've got, what we have so far is an average of like 1.6 planets per star. So we've only found one other star that has 8 planets like ours, but we found a bunch that have like 5 planets, some that have 3, some that have 6 and 7. So it seems pretty common to have more than one planet. And also, a lot of the ones where we've only detected one planet, there may be other planets that we can't detect because they're too small or they're too far away or maybe they're at the wrong angle. So just because we haven't detected planets doesn't mean that they're not there, because our methods are biased towards certain types. And then the other thing is there is something, for every star, there is something called the habitable zone. This is also known as the Goldilocks zone. And this is the area around a star where it's not too hot and not too cold. It's just right for liquid water. So, around a star, there's a ring where if it's closer in, it's too hot and water is going to boil and evaporate. And if it's farther out, then water is going to freeze. So Earth, we are in the habitable zone of our star. Luckily for us, we wouldn't be here if we weren't. We have not found many planets in the habitable zone. We found them more inside of it, right? I said that we find planets mostly really close into their stars. So mostly they're inside the habitable zone. Not in the habitable zone, but inside of it. So if a star is like a bigger, hotter star, you're going to have a farther out habitable zone, right? You need to be farther away for water to not evaporate. If a star is cooler, you need to be closer in, and it's going to have a closer habitable zone. It needs to be closer in for water to not freeze, right? Does that make sense? Okay. So that's the habitable zone. The cooler your star, the smaller in your habitable zone is. The bigger, hotter your star, the farther out it is. So looking at some of these homework questions about exoplanets, we can look at 21, which says, which of the following techniques are used to detect planets orbiting other stars other than the sun? So the first one says measuring small periodic radial velocity variations in the exoplanet host stars. Is that true? This is problem 21. Yes, that is true. That's that radial velocity method, where we look at the wobble, how the star itself is moving or moving around its center of mass. For some big planets, the center of mass is outside of it, and the star is actually going, in a circle. So measuring small changes in the total light from a host star when the exoplanet passes in front of the star.
Yeah.
True. That's that transit method. Directly imaging exoplanets orbiting their host stars. Yeah, we can direct image. And then using the boost in brightness of a background star when an exoplanet passes directly between the back star and the Earth and gravitationally lenses the star. Do we do that? Right, that's that microlensing. So all 4 of those are ways that we detect exoplanets. Which of the following are true and which are false regarding what we know about exoplanets as of June 2017? Although we have now discovered many exoplanets, to date we have not found another system with more than one planet. That's false. We found quite a few that have more than one planet. The most common type of exoplanet discovered to date is approximately half the mass of the Earth.
False.
That's false, right? So this says June 2017. I know as of now, it's Jupiter's that are most common. And I think that is what is, yeah. So most exoplanets discovered to date are very close to or in the habitable zone of their host stars. That's false, right? Most of them are inside of it. So we found a couple in the habitable zone, but not very many. The majority of exoplanets discovered to date have been detected via the light curve / transit technique. That's true. That's that Kepler mission that detected most of them. And then 23 says, which of the following statements are true and which are false regarding the habitable zone for exoplanets? It is the region in possible orbits for exoplanets where the temperatures allow for liquid water. That's true. For smaller mass, cooler stars than the sun, the habitable zone is closer to the star. True. For a given mass exoplanet, it is easier to detect the planet in the habitable zone of a low mass star than to detect it in a higher mass star. So that's true. And it's true because I told you that it's easier to detect planets that are close into the star. For a low mass star, the habitable zone is also close in. For a high mass star, the habitable zone is far away. So for a low mass star, it's easier to detect planets in the habitable zone because the habitable zone happens to be where it's easy for us to detect planets. Does that make sense?
Can you repeat that? The low mass star is...
The low mass star has a habitable zone that just happens to be where it's already easy for us to detect planets. Right? It's easy for us to detect close planets. The low mass star has a close-in habitable zone. So it's just where we're already detecting planets easily. For a high mass star, the habitable zone is far away. We're not detecting planets out there already. So it's not going to be as common to detect them in the habitable zone. And then the only planet known to exist in the habitable zone of a star is the Earth. That's false. We found a couple other ones that are in the habitable zone. Okay, so that is it for exoplanets. So we talk about, do you guys want me to talk about the cosmic microwave background before I do inflation, or are you comfortable with cosmic microwave background? Talk about it? Okay. So, as we look farther out into space, it's like we're looking farther back in time. And this is because light takes time to reach us. So the sun is 8 light minutes away from us. So light gets emitted from the sun and travels to us, and it gets to us 8 minutes later. So when we look at the sun, we're seeing how it was 8 minutes ago. Right? Does that make sense? Mm-hmm. So for stars, it's the same thing. If a star is 5 light years away, we see that star as it was 5 years ago. If a star is 1 billion light years away, we see that star as it was 1 billion years ago. If a galaxy is 3 billion light years away, we see that star as it was, or that galaxy as it was 3 billion years ago. So the farther away we look, the farther back in time we're looking. So you might think that so the universe is like 13.7 billion years old. So if we just look 13.7 billion years out into space, we could just see the Big Bang, right? We could just look all the way back in time to the Big Bang. And that would work, except for the early times in the universe, it was not transparent. The universe was not see-through. So when we kind of look back, the universe is expanding, right? So it's getting bigger as time. So here's now. And here's, some like the earliest stars forming and the early galaxies forming. So if we look back in distance and time to right here, we can see the earliest galaxies and the earliest stars forming. And then we look a little farther away, and we see something else. So back in time, before 380,000 years ago, the universe was filled with nuclei and electrons. All the atoms were broken up into their nuclei and the electrons. Most of everything was hydrogen, so mostly you have hydrogen atoms, which are protons, or hydrogen nuclei, which are protons, and then electrons just floating around. Right? You've got a bunch of your hydrogen nuclei and your electrons just floating around in space. And that's here. So the problem is, electrons scatter light. So when light passes through these electrons, it gets scattered around. And it gets all mixed up. Yeah. So whatever picture goes in comes out all mixed up. To the point where it just all the light comes in, it gets completely mixed up, and it all just looks the same. He described it as looking foggy, right? So fog does the same thing. Light comes into fog, and it mixes up the light, it scatters it around, and then when the light comes back at you, it's all mixed up, and it just looks like white fog, right? So this is what's going on in the universe at this time. We look farther back, we look back behind, farther away than the earliest galaxies, and we see this fog. So light from the earlier universe, that was emitted back this time, passes through this fog, gets all mixed up, and all we see here is this solid wall of fog. Right? It's behind the galaxies, and it's just a bunch of mixed up light. And it looks like just a big kind of wall everywhere. Every direction that we look, behind all the galaxies in every direction, is just this big, solid wall of fog. That's from these electrons bouncing around the light.
But it's probably not actually solid.
It's not actually solid, but it behaves as a solid. It's actually a plasma. But as far as its spectrum, it looks like a solid. And it's solid in the sense that we can't see through it. Right? So at 380,000 years ago, these electrons joined up with these nuclei and became neutral atoms. Right? These negative electrons joined up with these positive nuclei, and the universe became neutral. And it also became transparent. So now you've got your atoms, and the light just passes right through. So whatever comes in goes out, so it's transparent. Okay, so that's here. So we can see through this part, but once we get to here, the light's all mixed up, and we just see this wall of fog. So this fog is at 3,000 Kelvin. Or it was, 13.7 billion years minus 380,000 years ago, right? It was 3,000 Kelvin. And the light coming off from it had a wavelength that corresponded with that. So we had am I okay to erase this? Okay. In the very first part of the class, we learned about the Planck spectrum, right? And these continuous emission spectra. And they look like this, right? And we had a formula that says temperature is equal to 0.29 over the peak wavelength of this spectrum. So we can say, okay, this was at 3,000 Kelvin. We know the temperature. And we have, so that means it's giving off light at a specific peak wavelength. And then that light is traveling all the way from here, all the way to us. And as it travels, the universe is expanding. And when the universe stretches out, it stretches out that light too. So as this light travels, its wavelength gets longer. So it starts off like this, and then it gets longer and longer before it gets to us. So we see a different wavelength than was emitted by this, they call this the surface of last scattering. Right, it's the last time that these light waves, these photons, were scattered by the electrons. After that, they can travel straight to us. Right, so we can't see anything behind that. Yep.
Forgive me if this is like a dumb question or whatever.
No, dumb question.
So the light that we're seeing is from 380,000 years ago, or is that not
It's
a good
from
way to...
it's from 380,000 years after the Big Bang.
The Big Bang.
So it's like 13.7 billion minus 380,000 years ago.
Okay, for sure. But then it reaches us, and it's like the frequency or the wavelength that we see it, but it's not the wavelength that's actually being.
It was emitted at a certain wavelength, and as this light traveled to us, the universe stretched out, and it stretched that light with us.
Okay.
So
Thank you.
I got the biggest rubber band I own to try to show you this, but I can pass this around and you can look at it. So you may not be able to see, so I'm going to pass this around, but there's like a wave drawn on this rubber band. And as I stretch this rubber band out, the wavelength of this light gets longer, right? The distance between the peaks gets longer. And so the same thing is happening to this light. Space is expanding and stretching out, and it's stretching out the wavelength of that light. Do you guys want me to pass this around so you can look at it, play with it?
So the last scatter comes after the foggy wall.
The last scattering is the edge of the foggy wall. Right, we can only see the front of the foggy wall. We can't see through it to inside the foggy wall. So the last scattering is the edge of the foggy wall that we see. Right? So this light stretches out, and its wavelength increases by the time it gets to us. So we measure a wavelength that's longer than what it was emitted at. And when we plug our wavelength back into this equation, we get about 3 Kelvin, right? It originally was at 3,000 Kelvin, but because this wavelength got stretched out, we see it as a solid at 3 Kelvin. So this is everywhere we look, behind all of the galaxies, it looks like there is a solid wall at 3 Kelvin. It's really like 2.7, but it's essentially 3. And it's all basically the same temperature. Everywhere we look, it's this 3 Kelvin. There's some tiny little fluctuations. Some parts are like 0.00001 Kelvin hotter, and some parts are like 0.00001 Kelvin colder. And those fluctuations are really important, but they're really small. Okay? So this 3 Kelvin, this wavelength that we receive it at, is in the microwave range. So we call this the cosmic microwave background radiation, right? It's in the microwave range when it gets to us, and it's in the background of everything. It's behind all the galaxies, behind even the oldest galaxies. It's the farthest thing that we can see, right? It blocks anything that happened back in this time. The light gets scattered before it gets to us. Right, so this is the cosmic microwave background. This is also, like, you'll see it as CMB. And this is a huge discovery. Like, when they pointed microwave telescopes at the sky, and they were like, wow, literally every single place we look, there's these microwaves coming from behind the galaxies. And they've been able to measure it really well and measure these tiny little fluctuations, and they're really important. So these little teensy tiny fluctuations, these parts that are just a teensy tiny bit hotter or a teensy tiny bit cooler, are the seeds of what go on to form galaxies and stars and stuff. So the universe is expanding. So what at this time was these teensy little fluctuations, these teensy parts that were a little bit hotter or a little bit colder, also become a little bit denser or a little bit less dense. And places where they're a little bit denser, where you have a little bit more matter, that clumps together, right? Gravity pulls that matter together, and then it has more gravity as it has more mass. And so it can pull more things in, and then it has more mass, and it has more gravity, and it can pull more things in. And that's how you get stars forming and galaxies forming. They come from these tiny little fluctuations. They start off as these little seeds of little spots that are hotter and cooler, and then those spots that are a little bit hotter, the mass there clumps together, and that can pull other mass, and that's what starts to form the first galaxies and the first stars. Okay? Does this kind of make sense? Okay. So, questions on this? So we have to have these fluctuations in order for there to be galaxies or stars. Like if everything were the exact same temperature, then everything would be like exactly spread out and things wouldn't clump together, right? Like if everything is spread out and really uniform, then everything is pulling on each other the same amount. So if I have a particle here and a particle here and a particle here, it's getting pulled by the two on the outside, and it's not going to move because it's getting pulled equally. But if I have two particles here and one over here, then these two are going to get pulled together because the pull between them is stronger than the one over here. So we wouldn't have structure if it weren't for the start of it and these tiny little fluctuations. So for 16, a lot of this question is from a different part of this section, but I'm going to tell you they're all true. The abundance is, like it says, which of the following provides supporting evidence for the hot Big Bang model? The abundances of elements heavier than helium are lower than the solar values in old stars. I talk about it in one of the videos that I posted and then also in previous sections. The predicted abundances for helium 4, helium 3, helium 2, and lithium 7 at the time of element freeze out around 300 seconds after the Big Bang, max observations. That's something I talked about before. The presence of a ubiquitous background radiation characteristic of that from a 3K solid. That's this cosmic microwave background, right? We see it, so that's part of proof that our model is correct. And then fluctuations of about 1 part in 100,000 in the temperature of the cosmic microwave background. That is also true. That is we need those temperature fluctuations in order to form stars and galaxies. So then 17 says the temperature of the gas in the universe at the time it became neutral. So that's this time, right? The electrons and the protons combine together to make neutral atoms. At the time it became neutral was around 3,000 Kelvin. Why does the cosmic microwave background appear to arise from a 3 Kelvin source? What happened between them? Between when it was emitted and when we got it, the light.
The universe expanded.
Right. The universe expanded and it stretched the light out. The universe expanded by about 1,100 times. So when that light was emitted, the universe was 1,100 times smaller than it is now. And so the universe stretched out, and the light stretched out with it. So 15 says, what was the nature of the transition in the universe that occurred around 380,000 years after the Big Bang? So was it the end of the era of nucleosynthesis? No, that was about 300 seconds after the Big Bang. Electrons recombined with hydrogen nuclei, and the universe became transparent to electromagnetic radiation. That's true. That's what happened, right? That's what happened right here. You had all your electrons and your protons separately, and then at this time, they combined. The universe became neutral, and light could pass through them, and it became transparent. The first stars were formed after that. Quarks combined to make protons and neutrons before that. So that kind of leads us into inflation. So there were some issues with our model of the universe. Some things didn't quite make sense. And one thing that didn't quite make sense was called the horizon problem. And this is this idea that everywhere we look, this cosmic microwave background is the same temperature. We can look on one side of the sky and on the other side of the sky, and it's the same temperature. And we know generally that if you want two things to be the same temperature, you have to have them like touching or close enough to each other, right? If you have something really hot and something really cold, if you touch them together, the heat's going to flow from the hot thing to the cold thing until they're the same temperature. But if you keep them far apart from each other, then one's going to stay hot and one's going to stay cold, right? So things have to be close in order for them to be the same temperature. But we can say, okay, well, we know how fast the universe is expanding right now. And if we roll that back to the beginning of the universe, then those two sides of the universe, of the cosmic microwave background, were never close enough to be the same temperature. So why are they the same temperature? How do they know what temperature the other side is at? Right? So that's one problem. Another problem is that we didn't know what the shape, the geometry of the universe was. The universe could be something called positively curved, which means that it's kind of a sphere, but that would mean that the universe started and it got big, and then eventually it would collapse back down. And we know that that didn't happen because it would have already collapsed, and we're not all squished into a singularity, so that didn't happen. If the universe were negatively curved, it would expand too fast. So expansion pulls things apart, right? And gravity pulls things together. So in order for things to form, in order for galaxies and stars to form, on small scales, gravity has to be stronger than expansion. But if the universe were negatively curved, expansion would be so strong that gravity wouldn't be able to pull things together. So stars and galaxies and stuff wouldn't be able to form. So we knew that neither of those situations could be true. We had to have what was called a flat universe in order for the universe to not have done a big crunch and for the stars and galaxies to actually form. So we knew we had to have a flat universe. We knew that there was this horizon problem where the sides of the cosmic microwave background had to, at some point, have been really close together. We looked at these fluctuations in the cosmic microwave background and said, we don't know where those come from. How did that happen? Why are some parts a tiny, tiny bit colder and some parts a tiny, tiny bit hotter? And then there's also, the last one is there's this thing called a magnetic monopole. And physics says they should exist. No one has ever found one, but they should exist. So they must be really, really, really rare, right? They must have a really low density. Did you have a question?
What are they called?
Magnetic monopole.
Monopole?
Yeah. So like most magnets have two sides, right? There's a positive side and a negative side. So that's called a dipole. die for 2, a monopole would be like just a positive magnet or just a negative magnet. And we've never seen one of those. But physics says they should exist. They just must be so rare because we've never found one. So they had one solution that solved all of these problems, and that was called inflation. And this was the idea that way back in the beginning, the universe was really small, and really, really quickly, in a really short amount of time, it got much bigger, right? So, our expansion kind of goes like this, but there was a point where it got much bigger in a really short amount of time. So that allows the universe to have been really small at some point, right? If we just went this back to the beginning of the universe, then it would have to be this big. But if it had this inflation where it got much bigger really quickly, then it could have been really small at one point. And if it was really, really small, then those two sides that are at the same temperature would have been close enough to be in what they call causal contact. They would have been close enough to exchange heat and to equilibrate and to become the same temperature before they got blown out to the two sides of the universe, right? So it solved the horizon problem. It solved the flatness problem because anything that gets blown up really big starts to look flat. It's just like, so we know that the Earth is round, right? But from our perspective, the Earth is so big that to us, when we look outside, it looks flat, right? If we look outside, the Earth looks flat. So if you blow the universe big enough up, then it looks flat, and it solves our flatness problem where it had to be flat. The magnetic monopole problem, they had to be really rare. So if there were a couple of them around in the early universe, and then the universe blew up a lot and got a lot bigger, but you kept the same amount of monopoles, then they're spread out over a really big area. And it's a lot harder to just bump into one, right? So it started to make sense why we haven't found any. Because, there were, 3 of them here, and then it got blown up into this big. You spread those 3 out. If you say, oh, I'm right here, it makes sense that you haven't hit any of these, right? So it solved our magnetic monopole problem. And then the last problem that it solved was these density perturbations. These little tiny parts that are a little bit hotter, a little bit colder, a little bit denser, a little bit less dense. And it solved that by saying, well, when you're really, really small, when the universe is really small, there were these things called quantum fluctuations. And it's just a weird physics thing with quantum particles where you can't know too much about them. For a quantum particle, you can't know both where it is and how fast it's going at the same time. So there's some uncertainty in quantum particles. You know where it is, you don't know how fast it is. If you know how fast it is, you don't know where it is. There's this unknown quantity that causes these fluctuations. And they're really, really, really tiny. But just like if I put a bunch of dots on the, bunch of circles on the surface of a balloon, and then I blow that balloon up, those circles are going to get bigger. These quantum fluctuations started off on these teensy tiny quantum levels, and then this huge expansion, inflation happened, and it blew up those uncertainties into the temperature fluctuations that we see. So it explained the temperature fluctuations. So that's kind of the idea behind inflation. Early on in the universe, it was really small, then it got really, really big, really, really quickly, and then it's still getting bigger, but not nearly as fast as it got big in that one big inflation time, right? So it got really big really quickly, and it's getting bigger. And then one thing that we've discovered is that it's getting bigger at a faster rate. Expansion is speeding up. Not to how fast it was back then, but it's getting faster. And we know this by looking at older and older galaxies, galaxies that are farther and farther away. And we can see that they are expanding slower than galaxies now. So if the expansion was slower in the past and it's speeding up, then we know that expansion is speeding up. So, and eventually it's going to keep speeding up. Things are going to keep expanding. As things get less dense, expansion pulls things apart. It gets cooler, right? Temperature goes up when density goes up. And you're going to have less stars forming. There's going to be less gas and dust to go around to make stars because a lot of it will be used up to make stars already. And then also it's going to be farther apart. It's going to be less dense, and so stars are going to form less. So looking at the homework, problem 4 says a period of rapid inflation in the size of the universe at very early times can be used to resolve 4 problems associated with non-inflation cosmologies. What are those 4 problems? So there's the flatness of the universe. Expansion makes the universe flat by making it really big. The rareness of magnetic monopoles. So when the universe got really big, it just spread those couple monopoles around, and they're really rare. The origin of the density perturbations in the cosmic microwave background, which then led to galaxy formation. And that came from quantum fluctuations that got blown up. Did you have a question? The first part of that last one? Oh, the origin of density perturbations or temperature fluctuations. It's kind of the same thing, right? Because if density goes up, temperature goes up.
Is that one also like the seeds of the galaxy?
Yes.
So it has a lot of names.
Yeah. It's all linked, right? So these quantum fluctuations got blown up into the temperature fluctuations in the CMB, and those temperature fluctuations were the seeds of the galaxies. Right? So they're all linked. It's just you keep making this thing bigger and bigger and increasing this.
And that tracks back to him talking, that's the 1 in 100,000 parts.
Yes. Those fluctuations. So when they're on this scale, when they're on the scale of the cosmic microwave background, these fluctuations are in the scale of 1 in 100,000. Those temperature fluctuations and density. And then the last one is the horizon problem. So it's the uniformity of the cosmic microwave background. These two sides shouldn't be at the same temperature unless they were at some point really close to each other. And the only way they could have been really close to each other is if there was a big inflation.
So we could say temperature fluctuations that led to galaxy formations.
Yeah.
Is that fine?
Yeah. Right? I mean, you want to know that it's these temperature fluctuations led to density fluctuations, led to galaxy formation. But the temperature fluctuations did, in a line, lead to the galaxy formation. Okay? So, 5 says, what is the evidence for an acceleration of the expansion of the universe? So, this we get from looking at more and more distant galaxies, right? We can look, when we talked about expansion in the last part, we talked about Vesto-Slipher and Hubble and how they made that graph of expansion versus, or recession velocity versus distance. And they said the universe is uniformly expanding. But they weren't able to see really distant galaxies. And they weren't able to get good measurements of distance of these really distant galaxies. So they kind of just focused on galaxies that were closer to us. And as we get better technology, we can look at galaxies that are even farther away. And we can see that those were expanding at a slower rate than things are expanding currently. So what we look at, So in order to get good distances to really distant galaxies, we use supernova type 1 because they're what we call standard candles. So if you look at the light of a supernova type 1, you can tell its distance, right? They all have kind of the same way that they form, these supernova type 1s. They're all from a white dwarf that accreted mass until it got over the Chandrasekhar limit and exploded. And so we kind of know how luminous they should be, and we know the relationship between luminosity and distance and brightness. So we measure how bright they are, we know how luminous they should be, we can get a distance. So they are really good ways to measure distance. And so using these supernova 1s, we can measure distances to really far away galaxies. And when we get these really far away galaxies, we see that the universe was expanding more slowly in the past than it is now. So expansion is speeding up. 6 says, based on the current data and models, what is the most likely long-term fate of the universe? So eventual slowing of the expansion and a recollapse and a big crunch. False. That is if the universe were positively curved, we would have that. Ever-increasing expansion rate and a cold, dark universe.
True.
Yeah, that's true. This expansion is getting faster and faster. Things are getting pulled apart. The stars are going to run out. There's no new stars that are going to be formed. And it's going to be cold and dark. And then radioactive decay of matter will light up the universe as long as we can predict. That's not true. And then star formation in the galaxies will keep the universe heated and light for at least the next 10 to 20 years. That's not true. We know that star formation is decreasing. We talked about that in as part of the Big Bang stuff. Star formation peaked early on and has been decreasing. Okay, so I think that's all the expansion problems. Oh, so never mind, there's 2 more. So 18 says, which of the following describe the horizon problem in cosmology? So what did I say the horizon problem was?
When 2 places are the same temperature.
Right, when they shouldn't be.
When they shouldn't be.
They shouldn't have been able to touch or see each other. So that they were out of each other's horizon, right? And they are the same temperature. So that is the first one. The cosmic microwave background is at a uniform temperature over the entire sky, yet regions separated by large angles would not have been in causal contact in a universe that had expanded uniformly since the Big Bang. They wouldn't have been able to affect each other. So that word causal means, like a cause. They weren't able to cause an effect on each other and get each other to the same temperature if the universe hadn't had this inflation. So 19 says, the theory of cosmic inflation was originally motivated to understand why magnetic monopoles were so rare in the universe. What other cosmological puzzles does inflation resolve? That we appear to live in a spatially flat universe with omega total is equal to 1? That's true. We are in a flat universe. The energy released during the inflationary period that resulted in the formation of light elements, hydrogen, helium, and lithium? That's false, right? So that's talking the formation of light elements. That is the nucleosynthesis that happened over here. The growth of quantum fluctuations during inflation provided the small fluctuations in the cosmic microwave background that were the seeds of galaxy and structure formation. That's true. And then inflation allows us to understand what existed before the Big Bang. That's false. We can't go back any farther. We don't know what happened before then. Okay, so that is all of inflation. Technically, we're out of time. I don't have anything else to do. I can talk about dark matter if you guys want me to. If you don't have anywhere else to be, or we can finish up there.
I would like to hear about that.
Okay, no problem. Okay, I'm gonna erase this stuff. Because that's the only thing that's not covered in the other video, like the video I made at home last night about the hot Big Bang. So, dark matter, we found out that it exists in a couple ways. So the first way is what we talked about in the last section when we look at the rotation curves of galaxies. So when we measure for a galaxy, for every star in a galaxy, we want to look at the distance of that star and its speed, how fast it's going around the galaxy. And when we look at our solar system and we measure that for planets, we get something that looks like this. So for planets in our solar system, the farther away something is, the slower it moves. And we expected to see something like this for the stars in our galaxy. And instead, we got something that looked like this. We got this flat curve. And this didn't really make any sense. Because if you add up the mass of the stars and the gas and the dust in our galaxy, then you should be able to tell how fast things are going outside. You should be able to tell how much gravity they're creating, and that should tell you how fast things are moving. Or another way to think about it is, we talked about escape velocity, right? This is how fast you have to go to get away from something. So this is equal to the square root of 2gm over r. So g is a constant. So this formula tells us that as radius goes up, escape velocity goes down. The farther you are away from something, the slower you have to go to escape from it. So something in orbit around the Earth doesn't have to go as fast to get away from the Earth's gravity as something on the surface of the Earth, right? So radius goes up, escape velocity goes down.
I'm so sorry, can you repeat the example that you used about the example you just said?
Oh, yeah. So just so something that's in orbit around the Earth doesn't have to go as fast to escape from the Earth's velocity as something that's on the Earth's surface to escape the Earth's velocity.
So as like the general radius, not necessarily the radius of the thing?
Right, as the radius, the distance from the center of the gravity.
Okay.
So this would be the center of the Earth versus, like this would be the surface of the Earth versus some distance out in orbit.
Thank you.
Right, so, but in this case, for this galaxy, this would be like the distance from the center of the galaxy.
Okay.
So as you get farther away from the center of the galaxy, the escape velocity is going to go down.
Right.
So these stars out here, if we plug in the mass that we calculate from all the gas and the dust in the stars in the galaxy, these stars out here are going faster than the escape velocity. So they should be flung out into space and not be gravitationally bound to our galaxy, right? Does that make sense? So we know, since they aren't being flung out into space, that the escape velocity has to be higher than we think it is. And if the escape velocity has to be higher, that means there has to be more mass. So there is more mass in the galaxy than just the mass of the gas and the stars and the dust. But we can't see it, right? It doesn't interact with light in the same way that normal matter does. So they called it dark matter. It's this mass, it's this matter that's there, but we can't see it. So that was kind of the first scale, the first way that we detect dark matter. Then, when we look at clusters of galaxies, we see something really similar. Clusters of galaxies are orbiting around each other, just like the stars in a galaxy orbit around the galaxy. Clusters of galaxies orbit around each other. And you have little dwarf galaxies that are orbiting really fast. And if we add up just all the mass of the galaxies, then those dwarf galaxies should be going faster than the escape velocity of the cluster. They should be flung off of this cluster. but they're not, which tells us that there is more mass in this cluster than just the mass of these galaxies, right? There's always this more mass than what we can see, and we see it because things are not being flung off, right? Gravity is stronger than we think it should be, and gravity is stronger because there's more mass. So the last scale, so that's the scale of clusters. The last scale in which we know that we have to have dark matter is on the large scale structure of the universe. And this is kind of hard to draw, but when we zoom out and look at like all of the clusters of all of the galaxies in the universe, it kind of looks like a sponge, something, right? You have all these galaxy clusters coming off all together, right? These are filled with clusters of galaxies. And then there's these areas where there's not galaxies, right? And this is like 3D, right? So there's stuff coming off here, and then there's other stuff connecting here, and you have nodes here, right? So there's pictures in class, and I think I linked a picture previously. But it's this kind of interlaced structure of filaments and nodes and voids. These areas.
What are nodes?
Nodes are like kind of like where filaments join up together.
Oh.
So filaments are like these strings, and then when you have a bunch of strings coming together, that's a node, and then there's voids where there's nothing. Or not very many. You can have, maybe a couple galaxies. We actually kind of live in a void. So there's just a couple galaxies around us, I think. And when they do computer simulations of how this could have formed from going all the way back to that cosmic microwave background and those fluctuations that formed the first galaxies, and then those galaxies would form into clusters, and then they kind of run these computer simulations to see what the end result would look like. And the only way we get a structure that looks like this, that looks like what's actually out there, is if you include dark matter in your simulation. So if you run your simulation and you don't have dark matter, you get something that looks totally different from what we can actually measure out there. So that's the third way that we know that dark matter exists, right? There's on a galaxy scale, we see it in these flat rotation curves. On a cluster scale, we see it because these clusters are gravitationally bound together when they shouldn't be. And on the large scale structure, we see it because we couldn't form this structure without dark matter. So we don't know a lot about dark matter, right? That's kind of one of the huge things in physics, is trying to figure out what dark matter is. But we know a couple things about how it interacts with other matter. So it doesn't interact with normal matter in the same way that like my two hands interact with each other. They hit against each other. Dark matter doesn't do that. It has a small interaction cross section, so it can just kind of pass through normal matter. It doesn't interact with light in the way that a lot of normal matter does. So normal matter, you have like stars that create light. You have gas that absorbs light and re-emits light. You have dust that reflects light. So those all interact with light in different ways. And dark matter doesn't interact with light in any of those ways. The only way that it interacts with light is through gravity, through that gravitational lensing that we talked about. So dark matter, it still has mass, so it warps space-time, so light will bend around it, but it won't get emitted, it won't get absorbed by it, it won't reflect off of it, it just bends around it because of the gravity of that dark matter. And the other thing that we know about it is that it's what we call cold. It's not moving very fast compared to the speed of light. They've just done a lot of simulations and tested, because there's the particle called neutrinos that I talked about when I talked about fundamental particles. For a while they thought maybe dark matter was neutrinos, but neutrinos move really fast, and it just didn't fit with the simulations. Dark matter has to be slow moving compared to the speed of light. And so we also, when we say slow moving, we also mean cold. Or those kind of mean the same thing, right? We talked a lot about, on the inside of stars, when it gets really hot, things move faster and they can bump into each other. The opposite is true. When things are moving slow, that's cold. So, 3 says dark matter has been invoked to explain 3 observations on very different spatial scales. What are these observations? So the first one is on the galactic scale, this flat rotation curve. And we don't just see this in the Milky Way. We see this in every spiral galaxy that we look at. They all look something like this. They all have this flat rotation curve, so they all have dark matter in them. The second scale is clusters of galaxies. Clusters should not be gravitationally bound based just on their stars and their gas and their dust. You need more matter to hold the galaxy cluster together. And then the last one is large-scale structure. It wouldn't be able to form without dark matter. And then, so 7 says, which of the following best describes the large-scale distribution of galaxies in the universe? The options are uniform in all directions, clusters of galaxies, filaments, and voids, uniform except for small density variations at the level of 1 in 100,000, or completely random. So which one is this large-scale structure? Right, it's the clusters, filaments, and voids. So that uniform except for small density variations at the level of 1 in 100,000, that's the cosmic microwave background. That was the seeds of the first galaxies. But as the universe expanded, those tiny little fluctuations grew and grew and grew and grew to become these filaments and voids. And then which of the 8 says which of the following are thought to be properties of or true of dark matter? It is cold, i.e. it moves slowly compared to the speed of light. That's true. It does not readily interact directly with photons or other matter, i.e. it has a small cross-section for interaction. That's true. There's dark matter all around us, and we don't even know it's there because it doesn't interact with us. It does not emit or absorb electromagnetic radiation.
That's false, right?
That's true.
Oh, it's true, right?
So electromagnetic radiation is right. Yeah, light. So it doesn't emit or absorb light. And then it is primarily inferred by its gravitational effect on other matter.
Yes.
Yes, that's how this is a gravitational effect. The gravity holding the clusters together, that's a gravitational effect. Even the way it affects light, the only way it affects light is through gravity. Okay, I think that's, so there's a couple other questions that have one part that asks, dark matter is much more common than the type of matter that makes up stars, planets, and humans. And that is true. There's a lot more dark matter than normal matter. There's like the universe, if you break it up into what it's made of, no problem. It's like 70% this thing called dark energy, which also we don't know what it is, but it's what causes the expansion of the universe. So like 70% of it is dark energy, and then like 20-something% is dark matter, and then only like 5% is normal matter. So there's a lot more dark matter than normal matter. We just can't see it. So that 9 has one part of that, and then the rest is Big Bang stuff. And 20 is like half of the same question as 9, and has the same thing. Okay? All right. Well, good luck on your quiz tomorrow. No problem.